All right. Thanks guys for coming to another UTIG discussion hour. Today we have Ethan Conrad with us. He is a PhD candidate here. He did his bachelor's at the University of Florida and is now working on several different projects with several different advisors. But today he's going to be telling us about his work in Hispaniola, looking at the tectonics and structure and dynamics in the area.
Yeah, exactly. Thanks, Aaron. So the title of the talk today is Tectonics and Exhumation in a Tropical Transgressive System. And we're focused on the structure and topography of Hispaniola, but also zooming out of Hispaniola, a greater Antilles Caribbean island, to try to understand the regional tectonic evolution of the Northern Caribbean plate boundary. Okay. So here we have a regional picture of the tectonics of the Caribbean realm. The Caribbean plate is this zone in the middle here. It's a thickened lithosphere, likely a large igneous province. And the area of focus is the Northern Caribbean plate boundary. So this plate boundary is roughly 2,000 to 2,500 kilometer long zone of microplate block tectonics that's accommodating about 2 centimeters a year of convergence between the Caribbean and North American plates. This deformation is largely accommodated along 2 major fault zones, the Septentrional fault zone to the north and the Enriquillo Plantain Garden fault zone. And these curve into the Puerto Rico Trench and the Lesser Antilles, and then to the Southern Caribbean deformed belt where the South American plate meets the Caribbean plate. The objective of this is to investigate the relative contributions of tectonics, climate and surface processes to both crustal deformation and exhumation, as well as surface uplift, when we're thinking about how transgressive systems evolve in the long term. Like I said, we're looking through a lens of the Cenozoic evolution of Hispaniola and the Northern Caribbean plate boundary. And I wanted to divide the questions I have into process questions as well as sort of more regional questions. So the first question is related to strain partitioning and topography and how this relates to the rate of rock uplift and exhumation, all of these responding to various tectonic and climatic drivers. And we're focused on tropical systems here. So trying to think about this and comparing it with maybe more arid regions, for example, the Anti-Atlas or the San Andreas, where you still have transpression, but you have much different climates and perhaps different expression of the deformation and surface processes because of that. And the second question, not question 3, but 2, is how does deformation exhumation evolve as the plate margin goes from sort of a pure shear dominated, more convergent margin to a wrench dominated transgressive margin? Concerning the region, we want to understand how deformation and exhumation changes spatiotemporally in Hispaniola, and how this relates to this transition, this evolution of the North American Caribbean plate boundary. And then what is the nature of this transition from a subduction to a transformed margin? Because I know transpression may be a term unfamiliar to some, I thought it'd be good to give a brief introduction on what transfessional kinematics is. So it's simply when oblique convergence is accommodated by a combination of pure and simple shear. And this is typically foundationally modeled as a homogeneously deforming zone between 2 rigid blocks. And this framework was created in the 80s by a group, 2 scientists, Anderson and Marchini. And since then, this modeling approach has been taken much further to include strain partitioning or partition deformation, because in reality, the deforming region isn't homogeneously deforming. There's often brittle deformation within that zone. And some of the strike slip component of bulk strain is accommodated along either one boundary parallel vertical strike slip fault or pairs of strike slip fault. The type example of this is the Sumatra arc, where the Sunda plate, where the Australian plate is subducting beneath the Sunda plate, and you have most of the strike slip component of that deformation accommodated on the Great Sumatra fault, this boundary parallel large scale strike slip fault. So strain partitioning has some implications when it comes to exhumation or the bringing forth of rock from depth. So mainly when comparing wrench dominated and pure shear dominated transpression, you have relatively low amounts of vertical extrusion compared to very high amounts of vertical extrusion in a pure shear dominated scenario. So pure shear dominated would be, anything to pure convergence, where you have most of the material being extruded. And extrusion is important for exhumation, because exhumation is both bringing up the rocks through rock uplift and eroding away the surface through erosion. However, when you partition the strike slip component of bulk strain to some boundary parallel or subparallel fault, what you're doing essentially is localizing the pure shear component into these new separated domains. And this is exaggerating the amount of extrusion, of vertical extrusion, and thus exhumation. And the boundary geometry also plays a role when it comes to mostly the asymmetry of the deforming zone. So if you had two, more or less parallel boundaries, you'd expect a fairly symmetric deforming zone. Yet you could go all the way down to having inclined boundaries with different inclinations that would set some sort of asymmetry, some differences in the particle paths, and something we could track, possibly through geomorphology, is the motion of the drainage divide relative to these changes in boundary geometry, and using the motion of the drainage divide to try to think about the width of this deforming wedge, as well as its asymmetry. However, before we get into all of that, the Caribbean realm is a very complex tectonic region, and it's good first to talk about its evolution and some of the constraints we have from the literature on its evolution. So to do so, I compiled both geo and thermochronometric data, magmatic data, from the Greater Antilles and Lesser Antilles in some of Central America. And what you see when you plot these over the Greater and Lesser Antilles is a general younging to the east, across the Greater Antilles into the Lesser Antilles. This is reflecting the change from a former arc, what is called the Great Arc of the Caribbean, towards the initiation of the Lesser Antilles arc. And to walk through that, and then to also take these geo and thermochronometric ages and then plot them in their current day locations, except cut for each time. So whenever those geothermochronometers were set, I placed them in their current geographic location and then reconstructed that back. So around 60 million years in the early Cenozoic, you had the Great Arc of the Caribbean that was moving by slab rollback to the northeast. And you can see this incipient collision with the Bahama platform. This collision is about to change the system pretty dramatically and transfer subduction from the Great Arc to the Lesser Antilles. This collision happened about 50 million years ago. It's constrained by volcanic ages, the depositional record, as well as spreading in the Cayman Trough. And I'll get into some of those things as we move through. But after collision with the Bahama platform, you either gradually initiated a new arc, or you suddenly initiated the Lesser Antilles arc. And that arc began to roll back to its present day location, where there's active volcanism. So looking at the magmatic ages slightly differently, so this is looking at longitude across the Greater Antilles in age, we see this shutoff of volcanism related to collision with the Bahamas platform and the transition from subduction to a transform margin. And this seems to have happened between roughly 35 and 50 MA for Cuba and Hispaniola, and maybe a little bit later for Puerto Rico and the Virgin Islands. But we do see the initiation of Cayman Trough spreading, which is a hard constraint on sort of the motion of the boundary, because you have a large scale left lateral boundary, and that left lateral motion is accommodated by spreading of the Cayman Trough. So we also have constraints from tomography. There have been several tomographic studies trying to construct this slab architecture beneath the Caribbean plate. What we see here is two different tomographic models, one UUP07 and the other Texas 2015. And in both of these models, we can see some of this slab and this slab architecture beneath the Caribbean plate. So this slow anomaly in red here is showing the Caribbean plate, and these blue anomalies are showing the subducted lithosphere to depth below the Caribbean plate. And several authors, or a couple of authors, have used these tomographic anomalies to make interpretations about really what the slabs are doing beneath the Caribbean plate. And some have taken more liberties than others and included complex slab tears, which would have implications for maybe the dynamics of the overriding plate. But the tomography also provides some constraints on the amount of subducted material, and we're going to dive into those a little bit. This is some work I did when I was first starting, so I apologize for the horribly colored table. But I think it's an interesting exercise just to take tomographic anomalies, in this case, only above 0.5% deviation from the BP reference model. And I've made a few different paths for the way that the slab could sort of follow to get down there based on these fast anomalies, and use that to estimate the total amount of subduction beneath both subduction of both the Lesser Antilles slab or the North American plate beneath the Lesser Antilles, as well as Cocos subduction. And we're focusing here on Lesser Antilles. So from this, we can estimate about 1,260 kilometers of subduction at the Lesser Antilles arc. And this goes pretty well with some estimates that were made in the studies that I mentioned the slide before. Now, if we compare that with some popular reconstructions, they often show greater than 1,000 kilometers of Lesser Antilles rollback, since its initiation around 50 MA or late Eocene times. So if we take the location of the reconstructed location of the trench, and we track that through time to the present, and using the time between each line, we can reconstruct the trench velocity and the trench location through time and the total amount of trench rollback that would go with this model. And then we can estimate the North American plate velocity just using spreading anomalies from the Mid-Atlantic Ridge, and reconstruct the North American plate velocity. And from there, we can calculate the total amount of subduction, this being about 2,000 kilometers of subduction, so well over the estimates that were made just simply from measurements. And this plot on the right sort of shows a representation or interpretation of how this rollback and the accumulation of material would have happened. However, sort of a wrench in this is that in the Tobago and Granada Basin, so these are basins adjacent to the Lesser Antilles arc, and they should roughly record the extension of these basins as the trench moved and the slab rolled back. All we have is an extension record of about 70 kilometers. And this is taken from a seismic study where they just basically peeled away the post-Paleogene layers, reconstructed its pre-Paleogene width, and then figured out how far it had to have extended to accommodate those the new material. So from here, we can reconstruct the trench velocity from this Eocene study and the distance of trench migration. And then we can also, again, take the North American plate velocity and calculate the total amount of subduction. And this gets to about 1,400 kilometers, much closer to the estimate. And so this suggests that perhaps there wasn't as much slab rollback after the initiation of the Lesser Antilles arc. And this points towards maybe more of a spontaneous initiation of the arc rather than gradual transfer from the Great Arc to the Lesser Antilles. So rather than rolling back into the separating North and South American plates and then colliding with the Bahamas platform and transferring eastward, it collided with the Bahamas platform, subduction was shut off, and a new subduction zone was initiated. So returning to this regional picture of the Caribbean, let's think about the Northern Caribbean plate boundary specifically. So we're going to zoom in on the Cenozoic evolution of this boundary and its implications on Hispaniola. So after collision with the Bahamas platform, there's much uncertainty about what was exactly happening kinematically in Cuba and in Hispaniola during the transition. One idea is that you had this radial or fanning of strike slip faults across Cuba, going from the Pinar fault, which was this step fault subduction edge transfer and propagating margin that was part of the slab rollback story of the Great Arc of the Caribbean, transferring to the La Trocha, Cauto, and then eventually the Oriente fault. And like I said, a direct constraint on the transition is that this Cayman trough spreading began less than 49 million years ago. This is shown here on the panel on the right. This is just a simple geomap plot, but it's just showing this, the spreading of the Cayman spreading center. It's spreading at a rate about 12.6 plus or minus 6 million millimeters per year. And that's giving us some first order constraints on the kinematics of the transition. The issue is when you palinspastically restore the displacement on the faults and the spreading in the canyon spreading center, you have all this leftover space. And that leftover space is approximately 600 kilometers of material that needs to be accommodated somewhere in the greater Antilles in order for this for the space argument to work out. So there's two hypotheses surrounding this. One, that it's accommodated by subduction or underthrusting in central Hispaniola, and the other, similarly, rather than subduction and underthrusting or underthrusting, it's accommodated by strike slip. And so these things are going to be good to consider when I go through some of the data I showed that we've collected during our field work. So getting into the structure and topography of Hispaniola, this is just a digital elevation model, SRTM of Hispaniola and the quite striking mountain ranges on the island. And Hispaniola is unique in that it has both the highest and lowest point in the Caribbean. The highest point being Pico Duarte at 3,000 meters approximately, and Enriquillo Valley negative 46 meters. So you have about 3,000 meters of elevation change within 100 kilometers. And so it's an incredible amount of relief, an incredible amount of deformation that had to have occurred in Hispaniola in order to have this dramatic uplift story. I also want to point out some of the features I'll be talking about quite a bit in this talk. So the Cordillera Septentrional over to the Samana Peninsula is one of our targeted areas of study, as well as the Cordillera Central. And before these words, you see Massif du Nord, Chaîne de Mathieu. These are the Haitian terms for the same mountain ranges, but I'll be addressing them in the Dominican Republic terms, so the Cordillera Septentrional and Cordillera Central. So what we see here, and one of the benefits of this sort of artistic color map and hillshade approach, is that it really brings out the features, the topographic features in Hispaniola. And one circled here is, even from this perspective, this amazing left lateral offset in one of the drainage channels. And this is about 15 meters plus or minus 3 meters of offset. And this is just an example of the way that we can use geomorphology to constrain displacement of faults. And this is a classic way it's been done for generations to try to constrain deformation via geomorphology. Another geomorphic index we can look at, or another geomorphic tool, is swath profiles. So this is looking at a swath profile taken in this yellow box here. From northwest to southeast, we see a large valley in size. And this valley incision is related to a capture event that's recording the changing topography and deformation in Hispaniola. And so it has implications for understanding how the topography evolved in relation to both the climatic and tectonic drivers. So just as an example, if you take this 838 meters of incision, you assume a relatively standard or like average rate of 5 millimeters per year. This would mean that capture occurred 170,000 years ago, meaning that the topography is dynamically changing up until recent times. Getting into the late Eocene to Miocene evolution of Hispaniola, what happened tectonically in Hispaniola is just even more deformation, and this was imposed by, as I said before, you have the underthrusting and subduction, or perhaps subduction occurring in this thrust belt in central Hispaniola. But eventually you bring in a portion of uplifted Caribbean plate called the Bieta Ridge, and the collision and impingement of this Bieta Ridge into southern Hispaniola, based on this study, is segmenting that former continuous thrust belt into two thrust belts: the on-land Peralta thrust belt and then the offshore Muertos thrust belt. The collision had some structural implications as well. You see diffuse deformation and sort of the rotating outwards and tectonic escape, even at this small scale, as the Bieta Ridge began to collide with the arc terrains in Hispaniola. You see the formation of a large anticline, and that anticline was very apparent if you're looking at the digital elevation model, and some of the other structures in southern Hispaniola. To walk through this collision and evolution and what that had to do with the paleogeography, I'm going to show the results of a study by Huerta 2007, where he reconstructs the paleogeography based on the sedimentological record, as well as some structural work that they did there. In the early Eocene, it was largely carbonate platform. And then moving into the late Eocene, we have the onset of clastic deposition in this OC or Ocoa basin. So this is a hard constraint on the uplift of the Central Cordillera, is this deposition in this sort of piggyback Ocoa basin. Moving into the early Miocene, you have the progradation of a clastic wedge due to some regional tilting and structural control to the southeast out of the San Juan basin right here. And then it's starting to go down into this basin down here called the Azua basin. Moving into the late Miocene, we see a pretty interesting structurally controlled progradation of a turbidite wedge as the Bieta Ridge collides and starts to uplift portions of southern Hispaniola. And this is effectively channeling the clastic wedge out of the San Juan and Azua basin into the Enriquillo basin. And by the mid-Pliocene, you have the onset of subaerial deposition. And finally, to recent times, we have changes as the structure changes, as the topography began to evolve even more. And there's some this shows some analog models that show that collision and its effects just on sand, and how you can see the same segmentation of the thrust belt and initiation of this Muertos thrust belt and its division with the on-land Peralta thrust belt. Taking these constraints from the literature altogether, things that we discussed in the literature altogether, we can use G-plates. So this is a plate tectonic modeling software to do what's called a deforming plate reconstruction. And we can take the geometric and kinematic constraints, simply put them in as boundaries to the deforming zone and topologies within the deforming zone. And from that, we can triangulate a mesh and then tessellate deforming points. And simply the relative motion between each deforming point is going to give you strain, and from that, you can get crustal thickness. So doing so, I ran a model for the evolution of the Northern Caribbean plate boundary with those constraints. And what we see is the coalescing of crustal thickness in the central portion of Hispaniola as you collide the Bahamas platform and the Caribbean plate into southern Hispaniola. And this thickening and widening of the belt and the eventual thickening of the northern portion of Hispaniola is fairly in line with some gravity modeling work done in 2019, where they show around 40 kilometers of lithosphere around the Enriquillo Plantain Garden Fault, that southern major fault in Hispaniola, and relative thinning and thickening back towards the Septentrional. So this is fairly preliminary work, but it's promising to move forward with these types of models to try to think about how crustal thickness and strain changed throughout Hispaniola, given the constraints we have so far, and using that as a tool to go back and refine constraints where things aren't really aligned. Okay, so moving into results of this study, the study that I've been doing in Hispaniola, both the field work as well as some geomorphological analysis via DEM analysis, and thinking about what insights those results provide into the late Eocene-Miocene evolution of the system. So first, I'm showing the geology of Hispaniola. Hispaniola is characterized by this volcanic magmatic arc backbone that's going from the northwest to the southeast through Hispaniola, and rimming that is Miocene to recent sediments. And so what we did in our field work is we tried to have a cross-strike transect of samples so that we could think about the spatial trends across strike of the exhumation of these rocks in relation to the deformation of the Northern Caribbean plate boundary and also specifically Hispaniola. And we also tried to go across the trend of the Cordillera Central to see if there was any changes in the exhumation rate laterally that would suggest something about whether this transition from subduction at the Great Arc of the Caribbean to the Lesser Antilles Arc was continuous, or if it was sudden. If it was continuous, you'd see a gradual change in the exhumation of these bodies. Whereas if it was sudden, you'd see pretty much the same thermochronometric data from each of the samples collected. We also took several structural measurements in the field I'm plotting the sensitive slip vectors here. So keep in mind that I've reversed the thrust vectors because, you know, we measure the slicken line down in the down dip direction and we want sensitive slip. So I've flipped them over. But what that means is when you see the oblique or strike slip vectors, they're going to be flipped, even though they're both left lateral for thrust and normal faulting. So in the Central Cordillera, we've measured mostly two populations, seemingly overprinted populations of compression and strike slip. And the relationship between these is insightful when we're thinking about how the boundary evolved, considering strain partitioning and the evolution of strain partitioning as the boundary transitioned. And in the northern portion of the island, we again see an overprint, but in this case, it's again left lateral strike slip, but we also have this northeast directed extension component. So I'm showing a field photo from the outcrop circled here, and just to show sort of where these measurements came from, to have a look at the hanging wall footwall relationships and the gouge and the deformation fabrics that we're seeing in the field. And so here's just a little interpretation of the fault. So we have in blue the hanging wall being thrusted over the footwall here, and in white we have some of the gouge that's being sort of extruded out of the fault zone. And even having a closer look, we see a sort of 3/4 of an S-wing thick gouge layer. So that's a real measurement. And then we see some pretty nice ductile deformation fabrics that are corresponding to this large scale shear zone. And that's implying, based on the hanging wall and footwall relationships and the fabrics that we see, that this is a left lateral shear zone. Something we also did was we sampled for thermochronology, and I showed you where we sampled before. But before I get into some of the results, I thought it'd be good to sort of run over the basics of thermochronology for those that may not be familiar. So what we have here is a simple block model of a normal fault, showing the isotherms that would correspond to this model. And the isotherms are slightly deflected upwards because of the topography. But what we want to do is we want to track rock packages motion through these isotherms. And the way we do that is by following the concept of a closure temperature, or in this case, the partial retention zone. But for simplicity, we're going to collapse that partial retention zone into one closure depth. So this closure depth is the depth at which the mineral in the rock is no longer, the mineral in the rock begins retaining daughter product. And in this case, it's the alpha decay product, which is simply a helium, and that's why it's called helium dating. But so this closure depth can be simply calculated by the closure temperature. For example, for apatite, this is around 70 degrees C. And then you just divide that by the geotherm. So let's say 75 degrees C for apatite and a geotherm of 25 degrees C per kilometer. That gives you 3 kilometers for the closure depth. And then from there, you can calculate an exhumation rate, simply dividing that closure depth by the age. So if it was a 10 million year old date that you got from the rock, then you would have roughly 3 centimeters per million years of exhumation. And looking at the time temperature history of different cooling paths, you can see how different you could have different results you could have for example, a slow cooling path or a rapid cooling path, given a variety of thermochronometers. So we have apatite helium, we have zircon helium, and some higher temperature thermochronometers like argon hornblende. And so even though they're crossing at the same argon hornblende age, those lower temperature thermochronometers are giving us some key information on what's happened since that initial closure of the argon-argon system. And so for a rapid cooling path, you'd see a steep slope from present moving into time compared to a shallow slope for a slower cooling history. Again, I'm showing the compilation that I showed before of geo and thermochronometric ages, this time zoomed in on Hispaniola and also showing some of the locations we sampled for uranium, thorium, helium analyses. So this is basically a collection of uranium lead to argon-argon system geothermochronometers. And if you take a transect across the strike of the major faults, you start to get some interesting relationships. For example, in the north, you see younger ages exposed at higher elevations in this septentrional fault zone area. compared to in the central Cordillera, where you have even older ages exposed to higher elevations. So this is suggesting that there are some spatial trends in exhumation related to the differences between how bulk strain is partitioned to these different fault zones and the kinematics of the fault zones. So this would suggest that there's higher intensity uplift in exhumation in the septentrional fault zone, because you're bringing these rocks that closed more or less at the same depth to a higher elevation. From our data, so this is plotting all of the samples we collected for our fieldwork in 2020 and 2022. So all of the samples are shown in gray. These are the ones that are unanalyzed. The samples that have been analyzed, I'm showing in red, blue, and yellow. Yellow being uranium lead only, red being zircon helium and uranium lead, and then the blue showing where we have results for everything, both apatite zircon and uranium lead data. And just zooming in on a subset of this, because this is very preliminary. It's work that's really the analysis part of this work is really just getting started. I'm showing on the left here the zircon helium results, and on the right here the apatite helium results. And so crossing this fault zone, this Banao fault zone, we see pretty much the same zircon helium age. So this is suggesting that these thermochronometers cooled before displacement, and were later offset by the fault. And in the apatite results, we see strongly contrasting ages across that major fault zone. So looking at the distance along a swath profile shown with this dotted black line, and the elevation, if we draw sort of an isochron for the hanging wall block zircon ages against the footwall block zircon age, both around the range of 28 million years, that would give you 600 meters of offset on the fault. So this is an example of ways we can use thermochronology to constrain fault offset. And then the apatite results, where you have these young apatite ages juxtaposed against fairly older ages, is probably a result of the increased erosion, and thus increased exhumation in these higher elevations due to some orographic effect, or due to changes in lithology that's affecting the erodibility, and that I'll get into later. Concerning the geomorphology, this is showing the surface slope, so the gradient of the topography in the map on the top, and the surface slope is a metric that can be used to sort of qualitatively see where there's intense uplift and exhumation, because you can think about it, a slope or a scarp will be rejuvenated when there's uplift. So when there's continued uplift, you're continually rejuvenating that scarp. And with erosion, you're slowly eroding it away. So if you have no uplift on a fault that was previously uplifted, you're going to slowly wear it away. But if you have active uplift, it's going to continue to be steep. So these results are showing that you have most of the deformation, at least within the timescale of geomorphic analyses, so like tens of thousands of years, most of the deformations focused in this eastern portion of the Cordillera Central, as well as the southwestern portion of the Cordillera Central, and as well as in the uplifted regions of southern Hispaniola. On the bottom, I'm showing a swath profile, again, a cross strike of the major Cordilleras. And this is showing KSN, and KSN is a normalized channel steepness index used for similar purposes to see where deformation is localized within a region. And again, what we're seeing is high KSN values along the southern portion of the Cordillera Central, as well as in these southern terrains. So it seems that a recent deformation is certainly localized in these portions of the island. This map is showing the chi parameter. So the chi is a transformed parameter. It's generally used to understand the migration of a drainage divide. And so any asymmetry in your chi values. So for example, if you have a large asymmetry, red being high chi up in this small figure to the top right, and green being low chi, if you have strong asymmetry, you're going to have one basin, the high chi value being the victim, and the lower chi value being the aggressor. And so your drainage divide is going to move from low chi values to high chi values. And from this, we can start to look at how the drainage is moving in response to deformation in Hispaniola since that late Miocene collision. And it's seemingly moving to the southeast following the progradation of this Peralta thrust belt that I mentioned before. So as this thrust belt is prograding, it's increasing the asymmetry of the transfessional wedge because of the asymmetry and deformation and the localization of deformation mostly to the southwest of the central Cordillera here. And the result is that your divide is migrating further to the southwest. And that's a nice indicator that, that what we're thinking about as far as the spatial patterns of deformation are well supported moving forward. So bringing this into a hypothesis, so thinking about plate boundary transitions from pure to wrench-dominated transpression, my working hypothesis here is that the degree of strain localization will increase as the margin matures, and you develop this stronger structural and rheological anisotropy. And these zones are what's defining those morphoseismotectonic domains in Hispaniola that are drastically different in both lithology as well as topography. Applied to the region, applied to Hispaniola, moving from the Paleocene to the present, in this first stage of Paleocene to early Eocene deformation, the hypothesis is that you'd have most of your simple or your strike slip component localized in the central Cordillera, sort of this simple, like classic Sunda plate framework where you have a boundary parallel shear zone that's accommodating the strike slip component of bulk strain. Moving into the late Eocene to Miocene, you start to initiate this, this fold and thrust belt, at this point continuous. And you can see in gray here the beginning of the impingement of the Bieta Ridge, or this uplifted portion of Caribbean plate. And as it collides, you begin to localize more intense deformation in the southern portion of the island, and that thrust belt is prograding to the southwest. These stereo nets here show what we would expect to see as far as structural fabrics in the central Cordillera septentrional, as well as the southern terrains in Hispaniola. And then finally, the Pliocene to present, you have continued intense deformation in the southern portion of Hispaniola, but you also still have continued deformation in the northern portion of Hispaniola. And this is all mostly a seismically active region. The seismicity fairly similar to what we saw as far as geomorphic indices and the insight from geomorphic indices into deformation in Hispaniola. So getting into some hypothesized controls on this deformation and exhumation on more recent time scales, I want to think about to what extent climate and erodibility controls relief. So is there any marked difference between the deformation and relief in an arid setting compared to a tropical setting? And so is deformation responding to climate when the morphology of the mountain range is evolving? So here we see a precipitation map of Hispaniola. The approximate wind direction is these northeasterlies coming across Hispaniola through this this precipitation corridor, and it's divided by the Cordillera Septentrional and Cordillera Oriental as the orographic effect of those mountain ranges is drying out the winds as they below those ranges, but it's keeping moisture once you pass through that corridor, and it's sort of dumping rain on the western portion of the central Cordillera, and perhaps continuing to be like channeled through the central Cordillera, where you have some of these lower elevations. And the differences that this orographic effect can have as far as the microclimates within Hispaniola is pretty amazing. So on the left here, I'm showing what looks like a very tropical setting, somewhere where you have high amounts of rainfall. And this can be compared to another portion of Hispaniola in one of those red regions, where it's pretty much desert. It's very dry, very dusty. And so the orographic effect in Hispaniola, because of this really intense relief, like I said, it has the highest and lowest point in the Caribbean, creates these very diverse microclimates. And this provides a nice natural laboratory to think about what the effects are of this climatic gradient across the Cordilleras with relatively consistent deformation. So thinking about how is the uplift of the surface, which is really how is the evolution topography controlled by rock uplift, which I mentioned earlier as vertical extrusion, plus deposition, and then how is that material removed by erosion and compaction to form the topography we have. So this illustration comes from a great geomorphology textbook where you go in time 1, you have some mean surface height, and you go to time 2 where you have a component of uplift that would uplift that surface height to some theoretical position without any erosion or compaction or deposition. And that position would have been lowered by erosion and compaction and deposition to a new mean surface height. This one with more topography, you have valleys and peaks, and the valleys are being filled by the deposition of the eroded peaks. And that point, the path that a point takes from depth to the surface is its exhumation path. And so erosion at a point would be the lowering of the surface. Exhumation would be the point's path from depth, so some rock package moving from depth. And then the bottom panel here is showing a simple illustration to illustrate how erosion enhanced by this high precipitation and high humidity in a tropical system may work to localize fault activity. And this is just taken from a simple Moore-Coulomb failure criterion argument where you have sigma 2 and sigma 3 oriented so that you have a Moore circle that's just below the failure criterion. And then by removing mass above the fault, by reducing your sigma 3, which is vertical in this reverse fault setting, and pinning sigma 1, you're moving that circle closer to failure. And so by removing material above the fault, you may be able to reinitiate faulting. And so this is building in a positive feedback that I'd like to work through as I continue the talk. So this feedback is that you have more intense climate-driven erosion due to the tropical climate, and this is going to lead to strain localization. And this is because of the rheological weakness of the eroded rocks. And inspiration from this comes from 2 other studies in the Caribbean, one by Cochrane in 2017 and the other by Cruz in 2007. The Cochrane study was done in Jamaica, another apatite helium and zircon helium project. And they plotted the isochrons for apatite and zircon helium. And you see the curvature of the isochrons as you go towards the fault, suggesting that you have younger ages that would be at higher elevations as you approach that fault. And that path towards the fault is also paired with an orographic precipitation gradient. So you're increasing precipitation towards the Enriquillo Plantain Garden Fault, this EPGF here. And that's localizing the amount of uplift and perhaps feeding back into the deformation erosion system. And again, this one is in southern Hispaniola along the southern deformation belt. This is in the southern Caribbean along the southern Caribbean deformation belt, where this Cruz study shows relatively the same thing. So moving with the precipitation gradient, you see a younger apatite helium ages relatively at the same elevation. So they're all taken from sea level. And I'd like to return to the slope to think about these effects and their effects on the topography and geomorphology. And looking at the slope, and especially the central Cordillera, it's apparent that there's these much lower relief areas where you don't have as much surface slope, suggesting that either there's not as much deformation or it's just really high erosion. And these strikingly correspond to the location of granitoid batholiths in the central Cordillera. So this suggests 2 things. One, that they were mapped based on this, which is always a possibility because geologic mappers use a lot of different tools to map. But the other option is that the lithology is controlling the relief. So the granitoids, and from the field work that we've done, we've seen that these are really erodible rocks, not very resistant. They have a low K value when it comes to their erodibility. So it's possible that they're perfect locations to erode a lot of material away. And thinking about this corridor that's coming through the central Cordillera into these lower areas, it's going to only intensify the amount of erosion. And then I'm showing KSN this time in map view. So again, KSN is a channel steepness parameter used to understand deformation and exhumation relative to how the channel would respond to the uplift. And so what we see, and similar to the surface slope, is high KSN values on the southeastern portion of the Cordillera Central, and then high KSN values in the San Juan Los Pozos thrust belt, this formerly Peralta Muertos thrust belt that was later segmented. So this suggests that there's active deformation, but what we also see is very high KSN values in this region here, which is where that precipitation gradient is coming through. So maybe the combination, this feedback between high levels of erosion and perhaps the localization of deformation due to this high level of erosion is intensifying the amount of deformation along these faults. And then finally, as I close the talk, I want to talk about maybe a negative feedback that erosion and deformation have on each other. And so erosion-driven mass redistribution, when we're thinking about the broader evolution of a wedge, the broader deformation within a wedge, it may lead to more distributed partitioning of the pure shear component, that extrusion component, which would lead to broader patterns of rock uplift in areas of high climatic intensity. So without an along strike precipitation gradient for exhumation ages, for thermochronometric ages or exhumation rates, you'd expect young or fast ages where most of your deformation is localized. So if you're localizing deformation along one fault and that one fault is controlling most of uplift, in the near field of that fault, you would expect to see the youngest ages. And you'd see the oldest ages where you have more distributed deformation, where there's less of that pure shear component is spread out wider across the wedge. However, if you had a precipitation gradient where you had an increase of climatic intensity, you would be exposing younger ages at the surface than where there were without this intense climatic activity. And you'd also be moving mass out of the system and in different parts of the system in a way that you're, because of this climatic intensity and feeding back into this erosion, you're widening your orographic effect. You're able to move more mass in wider areas across the wedge. And this may result in changes in both the thermochronometric age, but also changes in the exhumation rate. And so this would be a direct feedback that climate and erosion could have on the deformational patterns we see. And in order to work forward on this hypothesis, we're going to do more analyses on some of the thermochronometric data that we've collected so far and see if we see some of these same trends. But what we do have is some continued geomorphic analysis. So I'm again in the northern Cordillera, this Cordillera Septentrional, and in the small plot to the right, top right of the left panel, you can see the mean annual precipitation rate for the Cordillera Septentrional, and you see this strong climatic intensity change or precipitation amount change as you go across the Cordillera Septentrional. And so this is acting as a nice place to analyze how a precipitation gradient may be changing the topography and what does that suggest about the deformation. And so taking swath profiles shown in the top panel across strike of the Cordillera Septentrional, we see very significant changes in the topography. In the first swath, we see very steep topography near the fault. So it seems that deformation is mostly localized here, and you have the most amount of uplift in this one zone, and it's roughly at 1,000 meters of elevation. Moving further to the east, we still have around 1,000 meters of elevation, but that elevation is distributed along a wider region. And so this, to me, is suggesting that you are localizing some of these broader uplift patterns as you're eroding away and removing material from the system. Other geomorphic indices we can look at are local topography, or the difference between the highest and lowest elevation within a 500-meter radius. So you can change this radius to look at to try to isolate the trends you're looking for and the resolution you're looking for. And what we see is an increase in local topography and as you move further to the east. And local topography is another metric. So an increase in relief would be suggestive of an increase in rock uplift, and perhaps this is divided by different strike slip faults that are starting to localize drainages along those strike slip faults, suggesting that this negative climate and deformation feedback may be existing in the northern Cordillera of Hispaniola. Surface roughness is another indice that essentially does the same as local topography, again showing these broader patterns of roughness, perhaps in relation to to this broader deformation signal that we see related to the climatic signal or the precipitation gradient across stripe. So finally, just to talk about the working hypotheses that I've gone through and some of the future work that I'd like to do. And I'm only showing hypotheses and future work for this final slide, since this is all very preliminary, and I thought it would fit well with the discussion hour. But the first hypothesis is that as you transfer from pure shear to wrench-dominated transpression, you're increasing the degree of strain localization as the margin matures, and you're developing a stronger structural and rheological anisotropy. And these will eventually define individual transfessional domains that are corresponding to tectonostratigraphic packages. So this is what I talked about in the beginning of the talk. And then further into the talk, I talked about these positive and negative feedbacks between climate and tectonics. So the positive feedback, man, my 2 and 3s keep getting mixed up here, but the positive feedback is that more intense climate-driven erosion due to a tropical climate will lead to the strain localization. So increased uplift in the near field of the fault, and this is due to the resulting rheological weakness of eroded rocks relating to this high precipitation, and also like very erodible rocks that are prone to high levels of erosion because of their lithology. And then the third hypothesis here is this negative feedback between climate and tectonics, so that by distributing mass through erosion and other surface processes, like by distributing mass through surface processes and erosion, this could lead to more distributed partitioning of the pure shear component and ultimately broader patterns of rapid rock uplift in areas of high climatic intensity. So moving forward, I'd like to do more thermochronometric inversion work. So this would be taking, rather than just plotting the data on a map or in the swath profile, this would be trying to reconstruct the time temperature history of the rock through a simulation that goes through a possible paths from depth to the surface and figures out which fits best with the constraints that we have. And then I'd also like to just dive a little bit deeper on the geomorphological analyses to try to support some of the hypotheses that I have more. So that concludes the talk. I'd be happy to take any questions or hear any comments or just engage in discussion.
Yeah, thanks, Ethan. That was awesome and clearly a lot of work. If you have any questions or comments, feel free to unmute yourself and go for it.
Ricardo.
Hi, Ethan. How are you?
Hey. Doing well, thanks.
Good, good. I'm in Potsdam, so I was following your talk. Very interesting, by the way. Thank you for sharing this data.
I didn't know I didn't know it was you, actually. I thought it was a different Ricardo, so it's good to hear you.
Ah, okay. sorry. Maybe it was a better one. I have few questions, maybe pure curiosity, not very question, but I agree about the effect, the precipitation effect on controlling the feedback between surface processes and tectonics. But I mean that amount of precipitation per year may be distributed over 12 months, or you may have some discrete events, very strong.
Yeah.
How do you think this change in precipitation may affect the feedback between erosion and tectonic deformation?
Yeah. So I think this is often like thought about comment and just phenomena when it comes to looking at precipitation data over years, because we know that most of the weather events that are resulting in this high level of precipitation is not really, it's not gradual over 1 year, like you said. It's in spurts. It's going with seasonal variations or large storms. So most of the erosion is actually occurring as a result of large storm events. And so to answer your question, I'm not entirely sure what effect this would have. I would think about maybe maybe more rapid change in the erosion would affect it. But to me, it's also still going to be integrated over thousands of years. So perhaps these changes are just more cumulative and on different time scales. But yeah, I'm not sure.
And do you think maybe the high KSM values may be also a response of this very strong event, and not only due to the uplift that is driven by tectonics? Because that's what we saw also in the lab. That's why I'm asking you, when you have few moments of high precipitation, you actually create canyons, but when you have distributed precipitation over hours, you have more, I mean, a diffusive erosion.
Yeah.
Also.
So I mean, I like that question. I think that's a great question, because it's something I wanted to emphasize too, is that this this precipitation corridor through the Cordillera Septentrional and Oriental could be continuing, or may have continued, through the Central Cordillera. And what we see is some very, the lowest slope, or the most carving of these basins seems to be within the sort of direction of that precipitation corridor, or like that precipitation channeling through the Cordilleras into the Central Cordillera. So I was also wondering, like, does this intensify the amount of erosion? So if this is facilitated by more separated high magnitude storm events, which are increasing the depth of the canyons and removing more of the mass, is that adding towards this feedback where you're taking mass off of the hanging wall block, in this case, in this reverse fault case, and would that help to localize deformation along the fault? So it's like amazing how there are many considerations you have to take when you're interpreting these data. And it seems to be that, you can't not look at lithology, and you can't not look at the precipitation, and you can't not look at the tectonics. They all have to be taken together to think about the entire story. And something I didn't mention, and I haven't done much work on, is this is a tropical system, and there's a lot of vegetation, and the effects of vegetation on slope stability, on some, and the results that you would have as far as the geomorphic metrics could be something significant, especially with these different microclimates.
Absolutely, yeah. And if I have time, I have two quick questions. Just tell me.
Sounds good, yeah.
Okay, perfect. The first one, you use for the KSN, you use a theta equals to 0.45, right?
Yeah. Yeah.
Did you check, did you estimate the best fit for the concavity index for, checking if 0.45 is actually the best reference theta in your case?
Yeah, so I did, for the Central and Northern Cordillera, sort of calibrate the MN ratio, or the curvature. However, I wanted to look at a regional picture and calculate KSN on the region. I think I had to use a constant theta value, because it would change fairly significantly from the different morphotectonic domains or different mountain ranges.
Sure.
Yeah, it's something actually Romano was mentioning as well when we were working.
Okay, probably. And the last one, since I agree with you. You said that this kind of surface processes are acting like tens, thousands of years. So yeah, are you planning to do some cosmogenics in the area for checking the incision rates?
I'd love to, but I don't think it's within, maybe after my PhD. I think I have enough projects right now, but yeah, I'd like to continue working in the Northern Caribbean if I could, and cosmogenics are a great tool for geomorphology. So that'd be really cool.
Okay, great. So Ethan, thank you for the nice presentation.
Thanks, Ricardo.
Yeah, awesome. I think that's pretty much all the time we have for today. So thanks again, Ethan. Great talk.
Thanks for having me. See y'all.